Ever get that
Yeah.
feeling, when you're looking up at the night sky and you just, you feel kind of small?
Oh, yeah, definitely. That sense of wonder, right? Makes you think about all the big questions.
Exactly. Where did it all come from? How did it all begin? And today on The Deep Dive, we're tackling one of those fundamental mysteries. We're asking, how long did it take for our sun to form?
A pretty big question, for sure. And it's not just about satisfying our curiosity. This timeline is really the key to understanding the whole evolution of our solar system and, ultimately how we got here.
Right. It all goes back to that. And for this deep dive, we're looking at some really fresh research, brand new findings just published in Nature.
Yeah, super exciting stuff. Based on some incredibly precise experiments, they were looking at the decay of a specific type of thallium.
Thallium, huh? So we're talking about nuclear physics here. That's pretty hardcore.
It is, but believe it or not, by studying this one element in the lab, scientists can actually gain insights into the birth of a star billions of years ago. It's like they're unlocking a cosmic time capsule.
Okay, before we get too deep into thallium and all that, let's set the stage. Before these new experiments, what was the prevailing theory? How long did we think it took for the sun to form?
Well, the general consensus was that it took tens of millions of years. And that estimate, it wasn't just pulled out of thin air. It was mainly based on the presence of long-lived radionuclides.
Radionuclides, those are just radioactive elements.
Yeah, exactly. And we find these radioactive elements in ancient meteorites, the really primitive kind that have been around since the very early solar system. They're like time capsules from that era.
So these ancient space rocks are holding clues to the sun's formation. That's pretty cool.
Yeah.
But where did these radionuclides even come from in the first place?
Good question. They were actually created in dying stars, specifically stars in their asymptotic giant branch phase, or AGB stars for short.
AGB stars. All right, go on.
So these AGD stars, they're kind of like the senior citizens of the cosmos. They're stars of intermediate mass, nearing the end of their lives. And as they go through this phase, they actually forge heavier elements in their cores, including these radioactive isotopes.
So they're like cosmic alchemists.
In a way, yeah. And when these AGB stars finally die, they expel all those elements they've created out into space. And this enriched material, it forms these massive clouds of gas and dust.
And eventually those clouds can collapse to form new stars and planetary systems, right?
Precisely. So these dying stars, they're actually seeding the next generation of stars and planets with the elements they forged. It's a cosmic cycle of life and death and rebirth.
That's mind-blowing. And so those radionuclides that were incorporated into our solar system, they've been decaying ever since, right?
Exactly. Over billions of years, they've been undergoing radioactive decay. And this decay, it's not just random. It follows very specific rules. So these radionuclides, we call them the parent isotopes. And as they decay, they transform into more stable daughter elements.
I'm following you. So how does all this help us figure out how long the sun took to form?
Well, scientists can measure the ratios of those parent radionuclides to their daughter products in meteorites. It's like looking at a clock that's been ticking for billions of years.
A cosmic clock trapped in a rock. That's incredible.
It is. And by analyzing these ratios, researchers can essentially back-calculate to determine when those original radioactive elements were first created and incorporated into the solar system. It's like piecing together a timeline of the sun's birth.
Yeah, so we're using radioactive decay to rewind the clock to the solar system's infancy. That's pretty ingenious.
Yeah.
You also mentioned something called S-only nuclei. Why are those so important for this whole dating process?
Right. That's a crucial detail. For the most accurate dating, we need to focus on radionuclides that were produced almost exclusively through one very specific process called the slow neutron capture process, or the S process for short.
Okay, the S process. What's so special about that?
Well, the S process ensures that we're looking at radionuclides that were formed in a very specific way. That way, we can be sure that we're not getting a mixed signal from elements created through other processes in stars or supernova explosions.
Because that would really mess up our timeline, wouldn't it?
You got it. And lead-205, or APABE, it's a perfect example of an S-only nucleus, meaning it was formed pretty much entirely through this slow neutron capture process. And that makes it a really valuable tool for dating the early solar system.
All right, or AP. Got it. So how does thallium fit into all of this? What's the connection between lead and thallium in this cosmic detective story?
The connection is in the way Oripabe itself decays. Now, here on Earth, under normal conditions, Oripabe decays into thallium-205 or Oripest. It does this through a process called electron capture.
Electron capture. What's happening there?
So imagine you've got a 4-pave nucleus, right? Inside that nucleus, one of the protons grabs an electron, one of its own inner atomic electrons.
Okay.
And when that happens, the proton transforms into a neutron. And in the process, it releases a tiny particle called an electron neutrino. This whole process is energetically favorable because of the specific way the adipose nucleus is structured.
So on Earth, lead essentially turns into thallium. But the research we're talking about today mentions a reversal of roles happening inside stars, like something's flipped.
You're picking up on the key point here. When we're talking about the environment inside AGB stars, we're dealing with extreme conditions. Temperatures of hundreds of millions of degrees Kelvin, and at those temperatures, things get really wild. Atoms are completely ionized, stripped of all their electrons.
Stripped of their electrons, so no electrons hanging around the nucleus.
Right. And that seemingly small detail, it has a huge impact on how these elements behave. Because without electrons available, adipose can't decay into adipoil in the same way it does on Earth. Electron capture just can't happen.
I see. So that decay pathway is blocked. But what happens to the thallium in these extreme environments?
Now, here's the really mind-bending part. Thallium-205, which is perfectly stable here on Earth, it actually becomes unstable in these stellar conditions. It undergoes a different type of decay called beta-minus decay.
Beta-minus decay.
Yeah, so in this case, it's a neutron inside the thallium nucleus that transforms. It changes into a proton. And during this transformation, the nucleus emits an electron and an antineutrino. And guess what? The end result of all this is that it forms radioactive.
Whoa. So it's like the decay process is reversed inside these stars. Thallium is actually producing the lid we use to date the sun's formation.
Precisely. It's a complete role reversal. And this is where things get tricky, because to understand how much radioactive was actually produced in those AGB stars, we need to know how quickly this ionized Orion decays. And that's something we can't directly measure in a lab on Earth. We just can't recreate those extreme stellar conditions.
So it sounds like we're at an impasse. How do we get around this problem? How do we figure out that decay rate?
This is where things get even more interesting. The researchers had to get creative, and they turned to a very rare and fascinating type of radioactive decay called bound state beta decay.
Bound state beta decay.
Yeah.
That sounds almost like something out of science fiction. What is that?
It is pretty exotic. So typically in beta-minus decay, the electron that's emitted by the nucleus, it just flies off, it escapes. But in bound state beta decay, something different happens. The electron that's emitted, it gets captured, it actually gets trapped in one of the empty electron shells around the newly formed IOI bion.
So it's like the electron gets stuck in orbit around the new lead atom.
Exactly. And this can only happen under very specific circumstances. In this case, it's because the nuclear decay leads to a very particular, slightly excited state of IOI, just a tiny bit above its lowest energy state, only 2.3 kilo-electron volts higher. And this specific transition, where the electron is sort of caught by the new lead atom, it's actually much more likely to happen in this scenario.
So we've got these two competing decays, lead to thallium on Earth and thallium to lead in stars. It's like a tug of war, almost. I think the article used a clever analogy to describe this, something about a stellar seesaw model.
It's a great analogy. Picture Eurytile and Eurypile on opposite ends of a seesaw. Here on Earth, that seesaw is tilted heavily towards Eurytile because Euryt naturally decays into it.
Right, that makes sense.
But inside an AGB star, imagine that seesaw tilting the other way. The extreme temperatures and the dense soup of ions, they can actually tip the balance in favor of Euryp. But the direction and speed at which it tips, they depend on a very specific factor, and that's the nuclear transition strength for this bound state beta decay of thallium. And before this experiment, that was a big unknown.
So this nuclear transition strength, this fundamental property of the nucleus, that's what these scientists set out to measure.
You got it. And to do that, they needed a very special kind of laboratory. They went to the Geosphere facility in Germany. Specifically, they used the experimental storage ring, or ESR, combined with their powerful fragment separator, the FRS. This setup, it's truly one of a kind. It's the only place in the world where scientists can create fully ionized heavy ions like ROTL, stripped bare of all their electrons, and then maintain them in that state for extended periods.
How long are we talking here?
They managed to keep those bare ROTL ions circulating in the ESR for hours, and while they were circulating, they could carefully study their decay. This allowed them to mimic the extreme conditions found inside stars, at least in some key aspects.
Hours under those conditions, that sounds incredibly challenging. The article mentions that this experiment took decades of work, and involved a huge international team.
It was a monumental undertaking, a real testament to human ingenuity and scientific collaboration. Professor Yuri Litvinov, the spokesperson for the experiment, he even said that the initial idea for this type of measurement, it was first proposed back in the 1980s. It took decades of development, of pushing the boundaries of accelerator technology to finally make it a reality. And then there's the team itself, scientists from 37 institutions across 12 different countries, all working together to make this happen.
It's amazing how much effort and collaboration goes into answering these fundamental questions about the universe.
Absolutely. They had to develop a whole suite of groundbreaking techniques just to pull this off. Producing those bare Urantil ions, separating them from all the other particles, accumulating them in the storage ring, cooling them down to extremely low temperatures, and then meticulously monitoring for those incredibly rare decay stints. Professor Litvinov even described it as a plethora of groundbreaking techniques, which, coming from him, carries a lot of weight. He's a giant in the field.
So after all that, they finally got the results. What did they find? What did this tell us about this nuclear transition strength we've been talking about?
It was a resounding success. They were able to accurately measure the rate of that bound state beta decay for fully ionized uratiel, a big breakthrough. And armed with this new measurement, Dr. Riccardo Mancino, a postdoc researcher at the time, he could then perform precise calculations of the decay rate of uratiel under those extreme stellar conditions.
So they finally had a number for how quickly thallium would decay into lead inside those AGB stars. What happened next? How did that connect back to the sun's formation?
Right. So then researchers at various institutions, places like Konkoly Observatory, the INF Osservatorio d'Abruzzo, and the University of Hull, they took those new decay rates and plugged them into their super sophisticated astrophysical models. Models that simulate everything that's going on inside an AGB star.
So they could essentially predict how much lead-205 would have been created in those stars.
Exactly. And not just in any stars, but in the types of stars that would have contributed to the cloud of gas and dust that eventually formed our solar system. This allowed them to predict with a much higher degree of confidence the amount of Colli-Orpib that was present in the early solar nebula. And that's a huge step. Dr. Maria Lugaro from Konkoly Observatory summed it up perfectly. The new decay rate, she said, allows us to predict with confidence how much Opергui Orbi is produced in AGB stars and finds its way into the gas cloud which formed our sun.
So they had this new, very precise prediction, and then they compared it to what we actually see in those ancient meteorites.
Exactly. And by comparing those two numbers, the predicted amount and the amount measured in meteorites, they could finally refine that timeline for the sun's formation.
Yeah.
And what they found was pretty amazing. Their calculations indicated that the sun formed over a period of somewhere between 10 and 20 million years.
10 to 20 million years. That's much more specific than the previous estimates of tens of millions of years. So this whole intricate experiment, it really did sharpen our view of the sun's birth.
For sure. And it gets even better. This new time frame, it's completely consistent with the timescales we get from looking at other CES process radionuclides in those same meteorites. So everything is lining up beautifully.
It's almost like different pieces of a puzzle falling into place.
Exactly. We're getting a more coherent and more consistent picture of the early solar system. And it all comes back to these incredibly precise measurements and calculations. It's remarkable how the behavior of atoms deep inside stars billions of years ago can tell us so much about our own origins.
The way all these different fields of science come together is truly inspiring. In the paper, Guy Leckenby, the lead author, he actually talks about the amazing collaboration involved in this work and how these very precise lab experiments can help us understand the hearts of distant stars.
Absolutely. It highlights the interconnectedness of science. To tackle the big questions, we often need experts from very different disciplines working together, sharing their knowledge, their techniques, and their perspectives.
So what's next? Is this the final word on the sun's formation timeline? Or are there still mysteries to unravel?
Well, this research, it's a huge step forward, no doubt. But the scientists themselves acknowledge that there are other nuclear reactions that play a part in the overall picture. You know how Ashimura accumulated in the interstellar medium before the sun even formed. One key area they're still investigating is how efficiently Ashimura itself can capture neutrons. They've actually got future experiments lined up at the ESR facility. They're going to use a method called the surrogate reaction method to further refine our understanding of these other important processes. It's an ongoing journey of discovery.
So there's still more to learn, more to explore. It's like we're peeling back the layers of cosmic history one experiment at a time. It's also important to acknowledge that this work is dedicated to several colleagues who are no longer with us, but who made significant contributions to this research over many years.
It is. Their dedication and their insights are woven into the fabric of this discovery, and it serves as a powerful reminder of the long-term commitment and the incredible spirit of collaboration that drives scientific progress. It's a legacy that continues to inspire.
Absolutely. So, for you, the listener, the big takeaway from this deep dive is that scientists, through some truly remarkable experiments, they've managed to refine our understanding of how long it took for our sun to form. We now have a much clearer picture of this critical period in our solar system's history. And the answer, based on this new research, is somewhere in the ballpark of 10 to 20 million years.
And it's incredible to think about how all this hinges on the behavior of atoms. Under the most extreme conditions imaginable, inside dying stars billions of years ago, it's a testament to the interconnectedness of the universe, how the smallest details of nuclear physics can unlock vast cosmic timelines. It's a beautiful example of how science can illuminate the deepest mysteries of our existence.
It really makes you think, doesn't it? If our sun took millions of years to form, what does that mean for the evolution of our solar system? What subtle but perhaps profound influences might that extended birth have had? Could it have shaped the formation of planets? Maybe even set the stage for the emergence of life? It's a question worth pondering as we continue to explore the universe and our place within it. So thank you for joining us on this deep dive. We hope it's sparked your curiosity and left you with some cosmic food for thought.
Until next time, keep looking up and keep asking those big questions.
And we'll be here to explore them with you.